So far, we have seen how LTI systems can be defined using their differential equations. And from that knowledge, we know that the differential equations can be of nth order depending on the highest derivative order. So now we will focus our discussion on first order circuit. That means where the highest order of the derivative of the differential equations will be 1. So we have already known that this is the general format of differential equations of LTI systems. And from there, if we convert the equation into a first order differential equation, so this is how the general form of the differential equation would look like. So, and this type of first order differential equations can be visible from practical cases when we have RL circuits. If we have RL circuits, so we have discussed it previously. In that case, the defining differential equations we have at our hand is a first order differential equation. And in the similar way, if we have an RC circuit, in that case, the differential equation that we have in our hand by providing every equation correctly, that is also a first order differential equation. That means for the practical case, if we are dealing with an RC circuit or an RL circuit, in that case, the defining equation of that system or of that LTI system we have at our hand is a first order differential equation. And that type of circuit is called first order circuit because uh, we have only one component added, either capacitor or inductor added to that circuit. So now we will see if we are given a first order circuit. In that case, the equation that comes into our hand would look like this, where yt will be the output. It can vary as we progress into the practical cases because yt can be Vt, I mean the voltage, or it can also be It depending on the case or the problem that we will be given to solve. So from that perspective, we can say that this will be the general equation for first order circuits, and after solving all the KVL, KCL, we will more or less we will have an equation like this. So now let us focus on how, if we are given this type of an equation, how we can solve it. From our previous knowledge, we know that the differential equations have a total response, where the total response has two parts. One is the natural response and another one is the forced response. So likewise, we will also solve this differential equation where we will consider one natural response case and another forced response case. For natural response case, we know that we have to think this equation to be like this. Like we will consider the input to the system is 0 or 0. We will consider this as a 0 input case. So let us put this as equation 1. So, and for the forced case, for the forced response case, we will have to consider the equation to be dft plus a y forced t is equals to, let's assume uh, the input here xt is a constant value a, so it will come here like a. So in both the case we have to assume some solutions, but here we will begin with the forced response case. As we can see, for the forced response case we will have to consider the input. Here the input to the system is a constant, so we can assume that the forced response of this differential equation or the system will be another constant, let's say k1. So if the forced response is k1, we can put this into the equation number 2. If we put it into the equation number 2, so derivative of a constant will give us 0, and we will have a k1 plus a. I mean, small a k1 equals to capital A. From there, we can conclude that the value of k1 will be capital A by A, and we can store this value. Okay. Now, what will happen to the natural response case? For the natural response, we have derived one equation, that is equation number 1. So, if we arrange the equation number 1, we initially got, it will give us this. If we rearrange it like d dt of y minus a y n t. Now look here, at the left hand side we have this thing. We can rewrite it in this way. Because if we differentiate uh, ln y and t, the output will be d dt of yn divided by yn. So we can replace this value by this one, and at the left hand side we will still have minus a. So now to remove this derivative, we can take integration on both the side. That will return ln y and t, and here the integration will give us at plus c. So now how can we remove the ln? We can take exponential at both the sides. So that will leave us with, as there will be exponential above, exponential's power will be at, and there is some constant involved, we can conclude that the total natural response will give us some constant into the exponential minus 8. So this is how we will have the natural response of the system in case of first order circuit. And we have assumed that the response of the forced case will be K1. So the total response of this case you can assume to be K1 plus K2 e to the power minus 8. We can conclude that if we encounter any first order circuit, from that first order circuit we will have a first order differential equation which will be generally in this order. And here we cannot define the yt to be vt or xt, vt or it, and xt to be vt or it, because depending on the situation we will uh, conclude with to a equation like this. So if we are given an equation like this, or if we can calculate an equation out of the circuit, given circuit, so in that case the solution will be something like this, where k1 is the forced response and this total value is the natural response of the given circuit or differential equation. Now, uh, now we can see that these cases can arise in only two set of cases. That is, we can either have RC circuit or we can either have RL circuit. So if we, and the solution here is K1 plus K2 e to the power minus 8. So for RC circuit, this value of A will be 1 by RC. And for RL circuit, this value of A will be R by L. If we have the value of R and C given to us, then we can replace this constant by these values from the circuits. Now, with the knowledge we have gathered for solving first order circuit, let us solve a few examples. Here we have one example given to us. Let us first go through the statement of the problem, what they have asked us to solve. Here it says that look at the circuit given in this figure, and they have asked us that assuming that the switch has been in position 1 for a long time, at t equals to 0, the switch moved to position 2, and we wish to calculate IT for t greater than 0. So this is the IT that we have to calculate for t greater than 0. And the circuit has two states. At first state, the switch was at position 1. So this would give us the circuit in this order. And at state 2, the switch moved to position 2. And this is the area of interest. From this condition, we have to calculate the value of IT. Okay. So look here at the condition 2, we can see that, or the state 2, we can see that we have to solve for IT. So we have to use KCL, and we can apply KCL at this junction. So that will, if we assume that the voltage at this junction is VT, so applying KCL here will give us VT by R1 plus the current through the capacitor, that is C dVT dt plus VT by R2. As there are no source involved at the state 2, so the equation's right hand side will be 0. To solve this KCL, we will obviously require the value of the voltage stored across the capacitor at t equals to 0. So this will be the initial condition for solving this differential equation. To look for this initial condition, we have to look at this version of the circuit. Okay. So at state 1, this is how the circuit would look like, and from this point we have to calculate the voltage between these two nodes, which will give us the voltage stored across the capacitor. I believe you all know how to solve the voltage available between these two nodes from the given circuit. Because this is a very simple circuit, and applying voltage divider rule, we can know that the voltage stored across the capacitor at t equals to 0 will be 3 divided by 3 plus 6, which is, or which we can say that will be 4 volt. So this is the initial condition for solving this differential equation, and this is the differential equation we have at our hand from the given circuit. So now we are ready to solve this problem. But look here by solving this problem, we will be awarded with the value of VT. But at the math, we have been asked to solve the IT. So once we have the VT, we can easily calculate the IT, as the value of the IT will be VT divided by RT. So now the stage is set from the differential equation, and the initial condition given, we can calculate the value of VT. So here we will apply the knowledge that we have gathered for theoretically solve any first order differential equation. So this is the setup. From here we can all uh, minimize the differential equation by putting the values of R1, R2 and C here, and that task is given to, that task is stored for you, and you can check after putting the values of R1, R2 and C, we will have our differential equation in this format: dv dt plus 5 dt equals to 0. So if we all minimize the task at hand, is that we will have to solve this differential equation for the initial condition given this. Now let us solve the differential equation. So the differential equation at our hand is dv dt plus 5vt equals to 0. From here we can rewrite this equation in this way: dv dt minus 5vt Or further we can rewrite this equation in this way, divided by Vt equals to minus 2. I think you can guess where we are going. We can rewrite the left hand side as d dt of ln Vt, and at the left hand side we will have minus 5. By taking the integration on both the sides, we can have ln Vt and minus 5t. So further, we can move that taking exponential, the power of exponential of both the sides. That will eventually give us the final output of Vt to be k2 e to the power minus 5. So now we have the solution with us. This k2 e to the power minus 5. So using the initial condition, we can find the value of k2. For this circuit, the solution appeared that Vt is equals to k2 e to the power minus 5t. And the initial condition, we know that at V0, the capacitor voltage will be 4 volt. So if we apply this, also V0 will give us k2 e to the power 0, which is 1. So this is what we will get. So from here, we can say that the value of k2 is 4. So if we apply this here, the final result we get, the solution of the differential equation we get is 4 e to the power minus 5t is the solution for Vt. The voltage available here will be 4 e to the power minus 5. So now what about the IT? So the value of IT here will be Vt by R2. And Vt by R2 will be 4 by 3 e to the power minus 5t milliampere will be the unit. So that is the solution of the math. We have another problem at our hand of first order circuit, and let us go through the problem statement and then we will look how we can solve this problem. So here it says that the switch in the network given in this figure, I mean at this circuit, opens at t equals to 0, and let us find the output voltage, this voltage for t greater than 0. So like the previous case, in this circuit we have two states. At one state, this switch will be shorted before t equals to 0. At t equals to 0, this switch will be open, so we will be having this circuit. So our area of interest is this circuit. We have to solve the circuit for we have to solve the problem for this circuit. So from this given circuit, I mean the problem statement, we can come to a conclusion that from the given circuit we can apply KVL in this loop, and that KVL will give us the defining differential equation for this problem, and solving the differential equation will give us the desired output. Let us apply KVL here. Here we can see the voltage related. There are four voltage related quantities. One is this, one is this, another one is this, and another one is this. And the current going through all of them are the same, that is IT. So applying KVL in this loop will result in minus 12 plus R1 IT plus R2 IT plus L DIT dt equals to 0. If we set all the values of R1, R2, and L into this equation, eventually we will have a polished version of the differential equation for the problem. That will be dit dt plus 2it equals to 6. See, we have come up with an equation, differential equation, where the key calculation will be made on it. So from if we have the value of it at our hand, we can easily calculate the v naught t, because v naught t will be it into r. So from the differential equation perspective, we have to solve this differential equation. And by solving this differential equation will give us the value of it. And if we have the value of it, we can easily calculate the problem that we are asked to solve, that v naught. So we have set our problem to some extent. We can say that uh, we have the differential equation. Now we have to find the initial condition. So for calculating the initial condition, we have to look back at the circuit for the state 1. So as we are solving for I, we need to find the value of I for initial condition. I mean, from this circuit, we have to find the value of I that is going through the inductor at t equals to 0, or just before the t equals to 0, and that will give us the initial condition. So at the state 1, this was short circuit. So we had a complex setup. From here, we have to find out the current that was involved with the inductor. So the setup is a bit complex. To make it simple, we can think of another method that we have encountered in our basic circuit course. That is, we can convert it into a Thevenin network looking from these two nodes. If we convert it into a Thevenin network for looking from these two nodes, that will give us the load for resistor connected here 2 ohm, and here we will have a very simple Thevenin resistance, and we will have a very simple Thevenin voltage. If we can convert our circuit into this way, from here we can calculate the current that will go through this path, and that will be the initial condition for current passing through the inductor. Now our task at hand is that we will convert our this circuit looking from these nodes and convert it into a Thevenin equivalent network. So if we do so, first of all we have to calculate the VThevenin. So here the circuit has been converted uh, into a simple form, looking at looking from these two nodes. So here we will have this part involved, and this is drawn here. Look here, from here we have kept this part open circuit, and from this perspective we can calculate the VThevenin. What will be the VThevenin? I think with the knowledge you have had so far, you can easily guess that the VThevenin here will be 4 volt. How? From this circuit, the total source voltage here will be 8 volt, this 12 and 4. And if we have this 8 volt and the voltage that will get divided across these two resistors, the voltage across these two resistors will be, this resistor will be 4 volt. Or you can think of it in other way by applying KVL. You can also come to this conclusion that the open circuit voltage here will be 4 volt. So that will be the VThevenin. And in the same way, we can look at uh, the same circuit from this perspective and calculate the RThevenin. For RThevenin, we have to think these sources will be shorted. So here we will only have these two resistors connected in parallel. And if 2 and 2 ohm resistors, these 2 ohm resistors are connected in parallel, that the equivalent resistance for this case is 1. So we can say that the RThevenin here will be 1. Now we can plug this RThevenin and VThevenin with the load resistor here, and we can have this circuit as a conclusion. And by solving this circuit, we can say that the current that flows through this path will be 4 by 3 ampere. Now we are ready to solve this problem. We have the differential equation required to solve this problem with us, and also the initial condition with us. So to solve this problem, we have the differential equation with us. That differential equation is dit dt plus 2it equals to 6, and the initial condition is that the 4 by 3. Now, with the knowledge we have gathered so far, uh, in terms of solving first order circuit, we can solve this differential equation and uh, get to the desired outcome. So, let us begin solving this differential equation. We have this differential equation with us. We know that the solution of the differential equation will be k1 plus k2 e to the power minus 8. As the input here is a constant, so we can think that the forced response here will be k1, or we can say that the forced solution of this will be k1. Now, if we put this solution into the differential equation, so the derivative of IFT will give us 0 plus 2 IFT will be k1 is equals to 6. From here, we can find the value of k1 to be 3. So one part of the solution is now at our hand. And for the natural response, we know that the equation will be di dt plus 2 it equals to 0. So from the experience, we can say that the natural response here will be k2 e to the power minus 2t. If we plug these two into the solution, we can say that the solution will be 3 plus k2 e to the power minus 2t. Now, from the initial condition, if we apply the initial condition, we can find out the value of k2. If we apply the initial condition here at I0, the value of the current will be 4 by 3, and at I0, the solution will look like 3 plus k2. From here, we can calculate the value of k2 as 4 by 3 minus 3. That will be most probably minus 5 by 3. So, for the final solution we have with at our hand is the IT will be 3 minus 5 by 3 e to the power minus 2t. And if we have the value of I naught with us, we can easily calculate the value of V naught by just multiplying 2 with this value. So this is how we can conclude this mathematical problem. Uh, for your reference, I will be uploading the textbook from where I have taken these problems. For your midterm exam and the quizzes, I will recommend you to go through all the example problems. To keep things simple, I am not adding the exercise problems, but you have to go through the example problems. So at the content section, I will upload the total chapter of the textbook from where I have taken these maths. Thank you.